Hello and welcome to Learn It from a Layman. This is Carl Christensen back again with Johnny Nielsen, or Johnny Hotcakes.
That's what they used to call me.
And Cameron Christensen, who's having technical difficulties, so may or may not be able to contribute much in this episode, but he's here in spirit. And Matt Christensen, who, if he doesn't contribute much to this episode, well, it'll be a very short, maybe Johnny can do some stand-up comedy for us.
I'm sitting down. Sorry.
Okay, dang. Well, then good. Glad we ruled that out. Okay, today we're going to talk about the laws of thermodynamics, which I had to look up the pronunciation of thermodynamics, so I am, of course, kidding, mostly. But suffice to say, you cannot become more layman on the subject than I, though I'm familiar with the idea of entropy, kind of, but it is confusing. So we're going to go ahead and punt the thermodynamic topic over to Matt, and we'll discuss it as we go. So, Matt, tell us a bit about the laws of thermodynamics.
Well, really quick, I'd like you to tell me a little bit about entropy.
There's these rabbits, you see, and nothing.
I think that's Watership Down.
Oh, Isn't that the same thing? Dang it.
Easily confused. All right. No. So yeah, what is your understanding of entropy?
The entropy that I'm familiar with is the idea of essentially. So in computer science, there is this idea of entropy. You want to maximize entropy actually when you're creating a model in computer science. There's a model called maxent, which is maximum entropy, because you want to be uncertain about your guess. So it's a law of uncertainty. So I'm assuming entropy has something to do with uncertainty and or disorder.
Yes. Okay. No, I was just wondering. That is a very lay definition, and it's good enough. It's disorderliness.
Right.
You can think of it as that. Anyone who's actually studied physics and is listening to this is like shivering right now.
Good.
Okay, so the laws of thermodynamics are a couple of things that the scientific community has accepted over the years, and they've been restated in different forms, but they're really important in governing our understanding of energy and what is possible with energy and energy manipulation. So there are three laws of thermodynamics that were initially accepted and understood. And then the community stepped back and realized, hey, we're missing a baseline definition here. And so they proposed a fourth law of thermodynamics. But because that fourth law was the underpinning of the other laws, it really needed to come first. And they didn't want to renumber all of the other laws. And so instead of making it the fourth law of thermodynamics, they have made it the 0th law of thermodynamics. No, I am not kidding. And
it makes a lot of sense to a computer scientist. You start counting at 0 anyway. So.
Yes, but that's not where we want to take our baseline from. But anyway, so you have the 4 laws of thermodynamics, the 0th law, the first law, the second law, and the third law. And all of these things basically tell us how the world works in terms of heat and energy transfer. Thermodynamics being a 2-part word, thermo, heat, and dynamics, motion, movement, transfer, change. So the laws of heat change. And entropy comes into play in that quite a bit, but I'm going to minimize that discussion because entropy is a difficult to understand concept that I don't like. So let's go straight into the laws of thermodynamics here. The 0th law is simply that if you have two systems and they are in thermal equilibrium with each other, with a third system. You have systems A, B, and C, and A is in thermal equilibrium with C, and B is in thermal equilibrium with C, then A and B are also in thermal equilibrium with each other. So you have three things. The first two things are the same temperature as the third thing. Therefore, the first two things are the same temperature.
Doesn't that?
You look at that and you kind of go, well, duh. And you should. But nonetheless, that's an important law to state, because without that law in place, you cannot have such a thing as a thermometer. Because your thermometer is supposed to be a gauge of temperature, is it not? If you're using it for any other purpose, I don't want to know. But the whole thing that makes a thermometer worth doing is that your thermometer comes into thermal equilibrium with whatever thing it's touching, and that gives you a reading on a scale. If you put the thermometer next to something else, it becomes into thermal equilibrium with that thing eventually. And because it is able to reach that thermal equilibrium consistently, and because the zeroth law of thermodynamics is true, that allows us to have that measurement scale and that measurement instrument. If we did not have the law, then the only way that you could scientifically prove that two objects were the same temperature would be to touch them together and see and wait for them to reach thermal equilibrium through their exchange of heat. That's the only way that you could prove that two objects were the same temperature. So it's a kind of facepalm and why do we need this thing kind of law, but is fundamental for the types of people who care about scientific proof that we have that one in place.
Okay, so speaking of proofs,
Woot.
I know relatively, well, not even relatively, I know precious little about proofs in general, but I know that physics and mathematics are complementary branches of stuff, of a thing.
That's
no?
some interesting language you're using.
Well, you know, okay, you use mathematics and physics a lot, is I guess what I was trying to say, right?
As well as in chemistry, biology, zoology.
Well, okay, some of those you use less math. Let's just
Urology.
say in physics, in theoretical physics, you better have a good understanding of mathematics, right?
Shopping.
Okay.
Yes.
So proofs in math are like they're a actual, like an equation, like you have a proof, right? Like this equals this, and that is a fundamental proof, and you have to be able to like mathematically take through the reasoning behind it. Is that the case with all of these laws?
Yeah, your laws of your truly accepted laws of physics have to be provable. Otherwise, it's a theorem. It's an idea. It's something that makes a lot of sense and no one has been able to disprove, but I cannot say for certainty that it is correct in every case because I cannot prove it. The laws of thermodynamics are laws because they are proven and provable. The zeroth law is important because it is fundamental to the provableness, that's a word, of everything else.
Okay, and so I guess what I'm trying to underscore or question, because I'm not entirely clear, but the idea that when we talk about something being provable or proven in the area of physics or thermodynamics, we're actually talking about mathematic proof, like not. Yeah. I've done a scientific study and I've shown over this large sample size that no, it's literally like I can take you through the mathematics of why this is the case, right?
Yes. Yep.
Right. So when
eventually you come to an equation that ends up saying 1 equals 1, and therefore this is true.
Right. Exactly. So when you see a lot of like movies or whatever where you get physics, geniuses, savants writing equations up on the board, a lot of those they're trying to get to the point where they can do proofs for particular ideas and laws to prove theorems, right?
Right. And other things. Okay, movies are definitely the best way to learn anything.
That's the only way I've learned anything in life. All right. Especially ones by The Rock. I learned a lot from The Rock.
I think we've derailed again.
Okay.
The physics of how your arms will never be that strong.
Yeah.
Yes.
We should do one of these where all of our discussion on the on whatever subject is just based on WWE catchphrases. So, all right, now if you guys will go ahead and get these hands, let's move on to the next
Okay.
law. All right.
Thermometers are true.
Thermometers are true. That is the 0th law of thermodynamics. All right. The first law of thermodynamics, which is number 2 on the list, one of the things with all of these, there's about 8 different ways to say them, depending on your scale of layman-ness and your the fidelity of your translation from the original French or Greek or German or whatever. So if you look up the definition of any of these laws, you'll get a bunch of different answers. And so I'm not going to quote anything, but I will describe what the laws are because that is universally agreed. So the first law of thermodynamics basically says that when you have a closed system with a certain amount of internal energy, the only way that you can change the internal energy of that system is to apply heat or work or matter or something into that system. And the change of the internal energy is equivalent to the amount of energy, work, heat, whatever chucked into it, minus the work, heat, or energy emitted by the system during that reaction. Okay, if you think about that and I restate it, it basically says that if you have energy X, you add energy Y, and you take out energy Z, your total energy is X plus Y minus Z. You look at that and you think, okay, well, that makes a lot of sense intuitively also. Why does that need to be a law? This is really just a restatement that of the law of conservation of energy, that energy cannot be created or destroyed, that when an energy reaction happens, the energy goes somewhere. It doesn't evaporate into the void. It is used, it is manifested in some form. It either leaves the system or is input to the system, and that change can be mathematically determined. An example, I have 5 buckets of energy. I chuck them into a light bulb. The light bulb emits energy in an equivalent amount. It will absorb 1 bucket of energy and re-emit it as heat. That's why when you touch a light bulb, it burns you. And then it chucks out 4 more buckets of energy as light. 1 plus 4 equals 5. That's all that it's saying. All of my buckets of energy went somewhere. Some of them went to heat. Some of them went to light. None of them evaporated into the ether. None of them were destroyed. And I did not get 6, 7, 8, 9, 10 buckets of energy out of that light bulb. I got an equivalent amount out. That is the first law of thermodynamics. The energy that you put into the system is equal to the energy that comes out of the system minus any change in the internals.
So does that Z in that equation, the idea of what percent or what amount of energy that doesn't get added to the system, is that dependent on the system itself or on the reaction, on the energy being put in?
Yeah, well, I mean, you can have, I should be more clear on this. Say I have a system that already has 3 buckets of energy inside it. I add 2 buckets of energy. The first law of thermodynamics says that I now have 5 buckets, and they have to be somewhere. The 5 buckets can stay inside that system. Maybe the output is 0, depending on what the system is and what it does. But if the output is 0, that means I still have my 5 total buckets. They're just contained inside the system now. Maybe the output is 5 buckets, and at that point, the internal energy of my system has dropped to 0. That's a theoretical, idealized case, but still, you could have that. What the first law is important in saying is that if I have my 2 buckets of energy that I want to put somewhere, and I have my system with 3 buckets of energy, the most that I can get out is 5. I cannot get 6. I cannot get 7, and 8 is right out. the number of buckets shall be 5.
Okay, but like in real world application though, but it's a lossy system, and that's Z, right? Z, like you're never actually going to get 5 buckets of energy if you add 3 to 2 in an actual real life scenario, right? There's going to be some loss.
So here we go into the nuances. The first law of thermodynamics says that the loss is part of that equation. It is part of that output. So when I gave the example of the light bulb, and I mentioned that you have heat that comes out of it, that's the loss. That's what we normally think of as loss. I can't do anything with that heat from that light bulb. It just makes my room hot. That's not what I want. I want the light. But that is where my energy went. Does that make sense?
Yeah.
Likewise, if I have my car has a bucket of internal energy. I fuel it up with gasoline, and I light the gasoline on fire, and I've given it 9 more buckets of energy. I now have 10 energy buckets in my car. My car is able to zip down the road at a speed and a velocity and a mass and a motion that is equal to the consumption of 5 buckets of energy translated directly into kinetic motion. What happened to the other 5 buckets? Well, they got lost as friction, they got lost as heat, they got lost as air resistance, they got lost as all of the inefficiencies in my car and in my engine, excess heat. That's why my engine is hot instead of normal temperature. That's where all of those extra buckets of energy went. But the first law of thermodynamics is saying that if I have 10 buckets of energy and I use 5 of them to move forward, I'm going to have 5 buckets of loss. I won't have 6. I cannot have 6. I cannot have more than I put into it plus what I started with. Does that make sense?
Yeah, it does. Now, I don't know how far we want to go into defining things. So energy is like the ability or potential to do work or something like that, right? Or
yeah, energy is. There's a lot of.
I don't want to go too far down the rabbit hole here,
but yeah, it is it is what you have in an object or transfer to an object in order to get heat or work or irradiance from that object. And we can jump into that maybe after we do this. We can talk about energy units and what they all mean, why you have things like watts and joules and coulombs and
yeah, that might be useful.
Things like that.
We can go ahead with the rest of the laws, but I think that would be useful because I think measuring energy is something that the layman like me doesn't even worry about, but it is.
But it shows up on your electrical bill.
Yeah, exactly.
And why do you have kilowatt hours, and what do those mean? So, okay. One of the consequences of the first law of thermodynamics, and this is going to ruin a lot of dreams out there, I can tell, is that you absolutely cannot have a perpetual motion machine that does more work than the energy that you put into it. You can't get infinite energy out of a device, no matter how you engineer it. It violates the laws of the universe.
Tim, you told me.
What about wives?
Wives?
Yeah.
This is not an area that I think would be wise for us to go into.
Oh, right.
Carl, cut this. Edit this out.
Yeah, as far as I know, wives, being the angelic seraphs that they are immune to most natural laws. However, thermodynamics still generally applies to them, I think. I don't know.
Next time we'll talk about the natural laws of marriage.
Woot.
There's only one there, and it's.
Yep.
I'm sorry.
Yep.
I didn't mean to.
All right.
Okay, Matt, continue.
So, second law of thermodynamics. There's a whole bunch of ways to say this one, including a bunch of stuff about entropy, but the really basic one is that when you have some water and you put it on a blazing hot pan surface, generally you will not see an ice cube form and the pan get hotter. because the heat that is in the water does not go into that blazing hot pan. The result would be, imagine you place some water in a pan that's on the stove. Would you expect to see an ice cube form out of that water with a lit burner underneath it?
No.
No, because that would mean that the water is transferring its own heat into the already hot pan. The second law of thermodynamics says that energy transfer does not go that way. It goes the other way. You cannot transfer heat from a cold object to a hotter object. It just does not happen that way.
It kind of like akin to the law, water flows downhill.
Yep.
Right. Energy flows towards its towards neutralization.
Well, yeah, it flows from hot to cold, essentially.
Okay.
So when I have my hot pan surface and I dump water on it, what I will see is heat will transfer from the pan into the water. The pan will actually cool down. The water will heat up. And if I leave them sit there and I turn the burner off and I don't add any more energy to it, both of those items will reach a thermal equilibrium with each other somewhere in between their two starting temperatures. The pan will cool to colder than it was, and the water will heat up to hotter than it was. And then they will sit at that same temperature, whatever it is, for all eternity, unless energy is further applied to it or taken out of it.
Okay, and the reason the pan cooled down is not that the water took some of its cold and put it in it, but some of the heat from the pan transferred into the water.
Yes, exactly. Yeah,
And
cold is not a thing that transfers.
Right.
Cold is the absence of heat.
And is this why and Matt, you could probably explain this better, but I remember you talking one time about problems of spaceships, like, rockets overheating, because there's no way to transfer heat off of it, right? Because they're in a near vacuum. Is that?
It's not exactly, well, kind of, I guess, maybe. That's more to do with heat transfer, which we can talk about more in a bit. But basically, in order for heat to transfer from one thing to another thing, there has to be some medium for that transfer. In general, that's not totally true, but in general it is. Turns out space doesn't really make much of a medium, so it's hard for an object to radiate heat. The only way you can do it is by radiating heat, and that is a much slower heat transfer process.
So when we think of something like a pan cooling off and radiating heat, a lot of what we're seeing is actually the pan heating the air around it.
Yeah, exactly.
As the air is the medium.
Yep.
Okay.
Yep. Now, true radiated heat, it really manifests itself as visible light. You only get an appreciable amount of it when you literally see something start to glow red hot. That's where you really notice an appreciable amount of radiated heat. Every other type of heat, if you wave your hand right over that lit burner, the heat that you feel is heat that is transferred via conduction if you're touching the burner, or via convection if you are through the air, as the air transfers the heat from the burner into your delicate fingertips. Don't do this. But when you look at that white hot, red hot, glowing chunk of metal, that is actually transferring heat directly into your eyes through radiated heat. It's not a lot of heat. It's a very small amount, but it is an energy transfer. Back to the second law of thermodynamics, though, the big thing is that energy transfer doesn't go uphill. Heat always goes from hot to cold. So the air is not going to spontaneously condense into liquid helium and liquid hydrogen around the fire, and the fire will not get hotter because of that. It will go the reverse. The burning surface will get cooler and the air will warm up.
Nice. Okay. Law 3 then?
Law 3, which is actually the fourth one.
Right.
So the third law of thermodynamics is weird, and this one matters, I think, a lot less to the layman or most people. But basically, there is a temperature called absolute zero. It is negative 273 point something degrees Celsius. It's really, really cold.
And it happens when you're on your way to work in the morning in wintertime.
You live in Arizona, Tim.
It gets so cold down here, sometimes there's frost.
He has a skewed perspective on many things, including thermodynamics. So,
We got our own laws of thermodynamics down here.
I'm pretty sure the state flag of Arizona has a perpetual motion machine on it.
And it's always radiating.
Yep. Anyway, absolute zero is defined as the temperature in which there is no molecular motion, because molecular motion, which we did not talk about, is the source of heat. If there is no molecular motion, there is no heat. It is really, really cold. You cannot actually achieve absolute zero, because the third law of thermodynamics basically says that the disorder, the entropy of a system, approaches a really small constant value. If it's a pure substance and it's not glass, it will be zero, as the temperature approaches zero. Well, okay, what does that mean to you practically? Not a whole lot, actually.
Matt, did I understand right? You're saying that a substance would approach a temperature limit, but that limit is not absolute zero?
Yeah, pretty much. You
So
just
we can't
get to
achieve
absolute zero.
We cannot achieve absolute zero.
No, you can get really close, but yeah, a corollary is that it is impossible by any procedure, and I'm reading straight from Wikipedia here, no matter how idealized, to reduce the temperature of any closed system to absolute zero in a finite number of finite operations. That was really stupidly wordy and just means you can't get to absolute zero. There is always some level of molecular motion.
Is there any? I mean, it sounds somewhat similar, though obviously very different in kind. The idea that you cannot achieve the speed of light, like we can get close to the speed of light, but we can't get there.
I don't know that would be related necessarily, but it is interesting that the universe does seem to put these types of limitations on us. You can't cool down until the point where there's absence of motion, and you can't speed up to the point where you can move faster than a theoretical wave in vacuum.
Right.
But a massless wave in vacuum.
So I have a question about this. How did they figure out the number, the negative 273, 0 Kelvin? How did they figure out that there would be no motion at that point if they can't reach that point?
I think that, well, I mean, it's always an approximation. It's not negative 273.15. It's negative 273.1, who knows what. But just if you're familiar with a lot with certain types of mathematical graphs of different functions, you'll see something called an asymptote. It's a value on the graph.
I don't appreciate that language.
Yeah, that's right.
Shut up. So the expression as y approaches 2, x approaches infinity. What that means is that if I have two values, x and y, and they're related somehow, as my y value gets larger and larger and larger and approaches 2, my x will approach infinity. Now, I can't actually get to infinity, can I?
Not that
I don't have that power, and neither do you.
Only
Maybe.
Buzz Lightyear can, but he actually goes beyond it.
Yeah,
That's right.
But what that means is that in order for Buzz Lightyear to get to 2, he actually has to get to infinity and beyond it. The rest of us mere mortals who are not space rangers will never get to 2 because we can't get our x to infinity. Likewise, you can see mathematical functions in nature that show similar asymptotes. So if I start cooling my object and I cool it and cool it and cool it, and I put infinite energy into cooling it, I can see that the temperature is approaching negative 273.15 Celsius, but it will never quite get there. That's the asymptote. And that's how you determine what that value could be.
Now, real quick, before we go any further, can I just put this out here? Can you guys just, for the sake of time, assume that about every 30 seconds, I'm stopping everyone and saying, that would be an awesome band name?
Please stop.
There's just too many.
How do I get him off?
Massless wave and vacuum. Imagine. Ladies and gentlemen, massless wave and vacuum.
And there's a way. I think I can mute him personally.
Oh,
hold on.
It's a...
Yes.
I think we should go back to
I muted him.
WWE catchphrases. All right.
Oh, I can also hit remove from call. Oh, goodness.
You're having far too much weird fun with this.
Oh, yeah, I do.
All right.
Wait, did I just unmute myself?
Yeah,
Yes,
you
you
unmuted
did. Good
yourself.
work.
Band. That's what you get. You just missed a whole bunch of cool band names. Too bad for you.
Okay.
Keeping them for myself.
All right.
Okay,
You
so
go name a band asymptote and see how well it does.
Yeah.
I'm sure we will get lots of media attention.
Yeah. Tim Cox
Okay.
and the infinite asymptotes.
once
all right.
again,
I hope
Going
you
back
delete
to
this
the-
whole section. Or
back
most
to
of
the
it.
laws of thermodynamics.
Oh, we're done with them.
Another
That's
good
it.
band name. Okay.
Right. Well, on the idea of the third one, though, and back to that idea, so is there? I know once we have theoretical ideas of what happens when we get to the speed of light. Obviously, they're all theoretical because we can't get there.
Yep.
Are there any theoretical implications of actually achieving absolute zero? I mean, nothing moves. That doesn't do anything, though, right? Like,
Well, it is a state where there can be no other type of reaction. There would be no chemical reaction. There would be no molecular motion. So what if I had some kind of highly toxic, reactive, dangerous, horrible, nasty substance? For some reason, I wanted to be able to use it, but only in certain specific conditions. And when I'm not using it, I need to store it somewhere. Well, if I can store it at absolute zero, then I know that it's not going to react with anything while it is cryo-cooled to that ridiculously low temperature. It can't react with anything. Other than that, I don't know.
Superconductivity. Don't some substances acquire superconductive qualities near or at absolute zero?
Oh yeah, well, yeah. At different temperatures, material properties change all over the place. You can get something called superfluidity as well, which is where if you put your fluid in a container, it doesn't just sit in the bottom of the container. It will creep up the sides of the walls of the container and spill out, which is kind of cool.
It is cool.
But yeah, I don't know. The practical purposes of absolute zero, you'd have to talk to an actual physicist instead of a layman like me here. The best I can do
have a
is...
question about that. If you are at absolute zero, does it stop all reactions, including like radioactive decay?
I don't know. I would imagine so, because your molecular and your atomic motion is halted. So I don't know.
Does that mean the
That's
electrons
interesting.
are stopped too?
That's a good question. I don't know as much about this as I should. I know that molecular oscillation is halted, but I don't think that would apply to electron orbits,
Yeah, that'd be
because then
subatomic.
they just... Yeah, I don't know.
Interesting, because I'd imagine it also has some implications in the quantum realm as well, though, given that all of that is theoretical and this is also theoretical, who knows? But like the idea of Well, I guess string theory recently was kind of debunked. So anyway, I did have a question though, as far as, okay, so applying this to something that people are kind of generally familiar with, or at least maybe have learned about a little bit in school, the idea of the universe either expanding or contracting, right? So the idea that either we're going to end up with all heat, all energy being used up, right? Eventually, our system will use up all of its energy, and we will just become a cold block of almost zero, absolute zero nothingness, right?
No. Actually, that violates many of the laws of thermodynamics.
I was going to say that.
Yes.
Well, so how does if the universe continues to expand, and I mean, stars burn out, you know, doesn't energy eventually become into a form that's no longer usable, I guess?
That is a more correct statement, because again, the first law of thermodynamics says I can't destroy energy. It's always there. But what I can do is put it in a state where it is equivalent, like that second law I was talking about, where everything is in equilibrium with everything else. And when I reach that point, then no additional reactions can take place because I'm at equilibrium. And in order to have a reaction, I would have to move energy uphill. The second law says I can't do that. So it's not that the whole universe is at absolute zero. It's that the entire universe would be at a uniform, 15 degrees Fahrenheit. It won't be that, but it will be at a uniform temperature and a uniform molecular composition and a uniform everything, such that no additional energetic reactions of any kind can take place. That is what people fear when they talk about the heat death of the universe.
Okay, so...
And that quickly gives rise to a whole bunch of nihilistic philosophies that I think are utterly bogus, and that I don't want to go into. Right. But yes, your life and your existence do have meaning. Don't worry about the heat death of the universe.
Speaking of the heat death of the universe, which I believe when we were in college together, we considered making a movie about, I'm not mistaken. But aside from that...
Brilliant.
With the other alternative, right, is the idea that the universe is contracting. And if that is the case, then what we end up with is everything heating up, right? Like, because it's compacting. Does that sound right? Does anyone?
I'll admit I haven't followed that theory and don't know about its implications. Johnny, you got anything?
I don't know.
They didn't teach that in medical school, Johnny?
No, we talk about it all the time in medical school. Urology, heat transfer, and the universe coming together.
Okay, good.
Band name.
Okay, I feel like I took astronomy in college, as did Tim, from the same teacher, who I believe was
probably
at the time
still teaching.
Look, if you want to talk about
time,
what all of this means to me as a Sagittarius versus you as a Cancer, we can have that separate discussion.
I'm just trying to get some implications that anyway.
Did you just call Carl Cancer?
Yes.
Okay, so we'll move on from that, given that I don't know the exact implications. I think the idea was that if the universe is contracting, you get back to the point where you're in a pre-Big Bang state, right? Because the whole idea is everything kind of combusts back together, and so the energy of the whole system comes back into one. In which case, that's massive, right? It's literally the whole energy of the universe compacted into one little particle, or whatever.
And Carl,
let me ask Matt this: if energy is lost as heat, then can you get it back?
I'll give a layman answer to that question.
Please don't say band name.
I got no idea. Well, I could say this, Johnny, just as this is just me kind of spitballing. You guys can tell me what you think. But I think the answer to that is, in some ways, yes. for example, that's what a lot of plants and microbial creatures do. They the sun is losing energy, right, from its fusion process and shooting that energy out across space, and then algae and grass and trees and so forth capture that energy and absorb it into a complex system of life that is then reabsorbed, by herbivores. It's then absorbed by carnivores and omnivores and so forth. So
yeah, but every time that transfer happens, some of the energy potential is lost. So when a plant undergoes photosynthesis, which is when it makes energy, it's basically making sugar, and then when the animal eats it, they're not going to get 100% of the energy from that sugar. They're going to lose some of its heat. That's why our bodies are warm, because they're going through these molecular processes where they're not 100% perfect, and so we lose this heat. And then some great white shark decides to eat me. Well, it's not going to get the 100% of like what I have put into making my body anyway. So there's always a little bit that's lost. The reason that the world just doesn't end is because we get energy input from the sun. So if we didn't have the sun, then life wouldn't happen, because you have to have that energy input to provide energy for all these different types of things. That's why, animals are so complex and can be, is because of the constant energy input into our system, which is the Earth. Anyway, that's kind of like what I understand, but.
Cool. Have you guys ever considered taunting a leaf of lettuce as you eat it? Something like, you may have gotten more energy efficiency, but I still win.
No, Tim. Nope.
Good. That's
COVID-19 downtime getting to you?
No, not at all. I'm just fine.
You ever taunted a piece of lettuce instead of talking to your children? Because I'm tired of that.
Just can't take it anymore.
Oh boy.
Take that, you terrible green leaf. I hope Matt comes back soon.
Taunting a piece of lettuce, band name, Tim?
Ooh, yes. Now we're rolling, see?
I think that's too long. Just taunting lettuce is probably good.
Taunting lettuce. Yeah, it's got to kind of roll off the tongue, yeah. I like that. It's the kind of name that people will be like, how on earth did they come up with that? I guess I'll buy their album.
So I think you all have to remember also, first off, you lose energy from the refraction of the atmosphere, going back to what Johnny was talking about, to the plants. But all that radiation is eventually collected back up and put into other things. It goes back into the black hole that collects everything, then that eventually becomes a new star after
I was actually going to
how many
bring
billions of years. So
I was going to bring that up. One of the things that I feel like I've read in the past, and I try not to read too much about black holes, because it's like studying in infinity. Eventually, you go.
There was
crazy.
Something I saw the other day. It was a kind of a timeline what's going to happen to the world in the universe. I think Google did it, or someone. Hold on, let me find that.
While you're looking that up, if you like, this is my question. If you have a piece of wood, it's basically a whole bunch of carbon bonds, and you can break those bonds and give yourself energy by burning the wood, and it gives off heat. And then you break all those carbon bonds, and you're left with ash, which is just carbon. At that point, you've let off all the heat. Can the heat be recouped, or is it like eventually, I guess it would just eventually equalize into the system, but that energy that was used to form the bond that is now broken, it's now heat, and can it be reversed? I don't know.
I think the answer would be not with any technology we have. I think the energy expended recapturing that energy would be more than the energy capture, right? Is kind of the plot hole in the Matrix, where they're using humans as batteries because human bodies produce heat, but the laws of thermodynamics dictate that the energy they would need to feed those humans to then capture the heat would be greater than that they would be losing heat out of the system. It wouldn't work. So I guess the answer is even these super powerful, highly advanced robots of the Matrix couldn't do it, so we can't either.
If a world without rules cannot do it, then we cannot do it.
That's right.
Yeah. So, I feel like the laws of thermodynamics, the proofs of thermodynamics, all of these things generally work in this idyllic scenario where Matt gave the equation earlier about X, and when you put 2 buckets of energy into a system that has 3 buckets of energy, you end up with 5 buckets of energy minus any amount that was used up in the transfer or reaction. That reaction is, I'd imagine, once again, as a complete layman on the subject, is almost never zero, right? There's always a loss involved, and so a loss into a form, not a loss of energy, right? Because the first law of thermodynamics, you can't lose energy, but into a form of energy that cannot be recouped. In any
an undesirable form of energy,
right? Like heat energy that is almost impossible to recapture in a usable way, and so I think that's the idea.
I was just looking it up, and looking up the efficiency of internal combustion engines, and it's saying that most modern combustion engines have a thermal efficiency of about 20% to 35%, with some of the really, really high-end ones achieving up to 35%, or there's like some diesel engines, like slow-moving diesel engines, that can get up to 45 to 54%. So, even the very, very best engines that we can make are losing half of the energy of that material, gasoline or whatever it is. And I suppose that's not even considering the fact that a lot of energy had to be expended to convert that, the crude oil, to pump it and then convert it into gasoline to use it in the system in the first place. So I guess it's kind of scary that our best go-to for energy conversion is, engines are so darn inefficient.
And so real world use cases of this. And so I'm just looking at the Wikipedia, which is how I get all of my knowledge. And it says and I remember learning this in college as well, the idea that entropy increases when you use energy. So the increase of entropy accounts for the irreversibility of natural processes and the asymmetry between future and past. So the idea that when we're using energy, we're increasing the entropy of the universe, which eventually these are irreversible natural processes which put the energy into a form that is not reversible. We're no longer in the state where we can harness that energy.
Well, you can decrease entropy, but it does take energy to do that.
Right. And like your fridge, for example, right? You're decreasing entropy inside of your fridge, but increasing entropy around your fridge. That's the idea of we're cooling off the inside, but we're on the outside. We are actually heating up.
Yeah. I think one of the best ways entropy was explained to me is if you have a room that you never clean, eventually it's going to be a disastrous mess. If you put your energy into it and clean it, then you can decrease that entropy, which is disorder. So you can order things, but it takes your energy put into the system in order to make it more ordered. Does that make sense?
Yeah, and actually, from personal experience, my bedroom once almost experienced heat death. My mom really got on my case.
Oh boy.
So I found it. It's the timeline of the universe from birth to death. This one was by Harry Everett. I thought it was by someone else, but I think that's the one. Time lapse of the future. That one's 30 minutes. But basically, about 10 trillion years from now is when the universe actually starts to stop expanding and collapse on itself.
That's cool. I'll set my timer.
Tell Alexa to set
Yeah.
a reminder.
Okay, Google. Yeah, set timer for 10 trillion years.
So yeah, it's pretty crazy. It kind of goes through all that. It's something about, what was it? It was about 13 minutes into it.
Okay.
That is pretty mind-boggling.
But
And
anyway,
on that,
yeah.
on that thought and on those time scales, I read once about black holes. You know, we talk about black holes being, you know, no matter can escape. But if you stretch the time scale long enough, even black holes will randomly, just due to random chance, occasionally emit particles. And so if you stretch the timeline long enough, black holes themselves aren't forever, you know. But again, it's a mind-boggling, vast, you know, amount of time.
You know, speaking of things that aren't forever, diamonds actually decay
What?
at a very, very, very slow rate, but they aren't forever. They will eventually become just nothing more than charcoal.
So, question:
False
If I'm
false advertising. I think it's a class
Right,
action lawsuit
fraud.
right in
There
the
we go.
making here.
They
Well,
are not forever.
if I'm shopping for a diamond, can I go to them? I'll be like, I'll look at it 1 week and I'll say, "What's the price?" And they'll quote me the price, and then I'll say, "Let me think about it." Can I come back a week later and be like, "Wait a second, diamonds undergo decay. This thing is a lower quality now. It's been a week," and like get them to lower the price?
I think the decay is a little slower than that. So maybe if you went
Shoot.
back in like 300 years,
Okay.
you could
So
talk it down.
here's another fun thing. In 762 million years, we will never have a full eclipse anymore.
Whoa.
There's something to think about.
762 million years?
So enjoy
Yes.
it while you can, people.
That's right.
Okay, I'll set a timer to enjoy my last eclipse. Alexa, set timer to enjoy last eclipse 761 million years from now.
Which is pretty close to when the sun gets too hot and kills all life on the Earth at 880
Alexa.
million years.
760 million years. Set timer to leave the planet.
So, you know, the eventual heat death of the Earth.
Cameron, stop. My calendar's full. I can't do it.
Tim can't handle more than one appointment at a time. You know this, Cameron. You know this.
That's right. I'm
So-
not a planner.
Yes, apparently because the sun increases luminosity by 10%, it increases the Earth's heat by 50%, or the temperature. So,
Well, shoot.
and Phoenix will now be 200 degrees, and you will die.
Oh, water world. Got it.
No, this goes past Wilder World. This so hot it kills everything.
I can only process things through popular movies.
It evaporates all the water.
What about cockroaches, though? I heard they're basically impossible to kill.
That's nuclear
Matt,
radiation.
We're to water world and cockroaches now. Save us.
Okay, somebody said nuclear. That's the first problem.
Oh,
So do you want me to just go into the basic energy measurement types?
sure. That'd be
All
great.
right, or units? Okay.
Yeah.
So your basic energy unit, and I'm only going to talk metric here because I am a reasonable person. I'm
I
not
would
going to
prefer
go into.
scientific versus
I want
metric.
cubits.
You want system international?
Yes.
Oui. Okay. So yeah, we're not dealing with British thermal units or horsepower or stone pounds per foot. But anyway, so your basic unit of energy measurement is the joule. It is analogous to that bucket of energy that I mentioned before. Imagine your light bulb. You want your light bulb to actually have some light, right? Well, you throw a joule of energy at it, and it reacts and generates about I don't know, 2/3 of a joule of light and 1/3 of a joule of heat, depending
Now,
on the
Matt, we should
efficiency of your bulb.
probably clarify, because we were just talking about diamonds. So we don't mean joule, Jewel. We mean Joule. Did I spell it right?
Yes, you did.
There we go.
Thank you for that distinction. So,
Hey,
for
I'm a
all you
layman.
laymen out there, please stop shoving diamonds into your light bulbs. It's not
This
going
thing
to
is
work the way that you want.
expensive.
Yeah. So getting rid of fractions. I have my light bulb. I want to make it light. I throw 3 joules at it. I get 2 joules converted to light, and I get 1 joule converted to heat. And then I'm done. And my light goes out, and I'm plunged back into darkness. So we have another energy-ish measurement, and we call that one power. And power is energy over time. It's a rate. It is the amount of joules that you chuck into something in a given amount of time. So consider your shower. You don't just want a liter of water to appear out of your shower. You want a constant flow coming out of your shower. You want so many liters per second. Likewise, with your light bulb, you want so many joules per second. The unit for that is watts. 1 watt is 1 joule per second. So my 60-watt light bulb is a light bulb that consumes 60 joules of energy every second, and it spits back out, I don't know, 40 joules of light and 20 joules of heat or something. According to the first law of thermodynamics, the amount that it spits out will always be 60 joules because that's how much I'm putting in. I'm sorry, it will always be 60 watts. It will be 60 joules per second at a rate of 60, and that is a rate of 60 watts. You can have different efficiencies for your light bulbs and for your systems and for whatever else. Your LCD bulb is going to give you way more joules of light and fewer joules of heat for an equivalent amount of energy. But all of your light bulbs and all of your machines and all of your systems, no matter what they are, will consume and change and transform and produce energy under that basic construct. You'll have a certain amount of energy that goes in, measured in joules, or you will have a certain rate of energy input measured in watts. And then you will have an output of energy in joules or watts, and the amount of the output plus the amount of the change on the inside will be directly related to the input according to that first law of thermodynamics. Does that make any sense? Yeah.
Yeah. So incandescent light bulbs are the least efficient. They emit more heat. LEDs and other kinds emit less. I know that, but do you know anything about the mechanics of how LED lights achieve higher efficiency? How do they work? Or does anyone know? That might not be.
It's just a more efficient chemical reaction at its core.
I have a question about dollars and cents with this. So if I am usually using a 60-watt light bulb and I go down to a 40-watt light bulb, is that going to make an appreciable difference in my power bill from month to month?
It depends how long you have the light bulb on.
Well, yes, it will. Okay. Let's assume that your power bill right now consists only of the electricity that you use for 60-watt light bulbs. Yeah, if you drop all of your light bulbs to 40-watt bulbs in exchange for living in a depressing dimness, which is what you get out of 40 watts, you will save 1/3 of your power bill because you are using less less electricity.
A third?
This is also
You'll
why
save
the
a third. You're only using 2/3 of what you used before, so you
Okay,
save.
Yeah, save a third.
Yep.
But this is also why the LED light bulbs make sense, and why the energy conversion matters, is because you're getting more light, so more of the energy is being emitted as light.
When you go and you shop for an LED bulb, it doesn't
you
actually
equivalent.
use 60 watts. It uses 8.5 to 9 watts. And what you'll see on the box is that it is advertised as a 60 watt equivalent. You don't want your LED bulb to use up all 60 watts. That would be stupid. You want it to use up way less watts, which it does, and produce the same amount of light, which it does. The way that it's able to do that is simply because it uses a more efficient energy transfer process. The electrical and chemical reactions that occur in a light emitting diode are more efficient. They generate more light and less heat than the chemical reaction that happens when you pump electricity into that little filament in your incandescent bulb. When you touch an LED bulb, you shouldn't do that, but if you did, it is still appreciably cooler than an equivalent 60 watt incandescent bulb. A 60 watt bulb will burn your fingers pretty quick. I don't know that from experience because I'm smart, but I've heard that.
You
You
have
can set your teddy bear on fire once from a 60 watt bulb.
Wait, what?
Heat death. That's
True.
called heat death.
Yeah, there we go.
Your Winnie the Pooh bear that we put in the lampshade, it caught on fire. And burned a
happened,
hole in
I
the
was there.
lampshade.
I do
It's a
remember
good
that.
day to die, muttered
Yeah.
Lou.
So if we had, thank you for remembering or reminding me how you assassinated one of my stuffed animals. If we'd had LED bulbs at the time, that little Pooh Bear doll might have gotten a sunburn, but he wouldn't have gotten the potentially house burning down scorch marks that he did. And it's all because of the efficiency of the reaction. Now, the reactions on both of them are in accordance with the law of thermodynamics, in the sense of when you have a 60 watt incandescent bulb, you chuck 60 watts of electricity into that thing, you get, say, 5 watts of light out of it and 55 watts of heat. Now you take your LED bulb, it uses 8.5 watts. You get the same 5 watts of light out of it with only 3.5 watts of heat. That's pretty cool. The same math works out. 3.5 watts of heat plus 5 watts of light is 8.5 watts, and that's what my bulb consumes. 5 watts of heat, or I'm sorry, 5 watts of light plus 55 watts of heat is the 60 watts that my incandescent bulb consumes. Both observe the first law of thermodynamics. The difference is simply that one is way more efficient and therefore uses less overall energy for its first law equation. Does that make sense?
Yes.
Excellent.
Yeah. So I have a question. How bright would a 60 watt, an actual 60 watt LED bulb be?
Oh, man was not meant to handle such devices.
You know those
Right.
cars you see going
Right
down
within
the
the sun.
highway and
I mean, you
blind
could-
you?
Yeah, you could do a very rough extrapolation with this. If you have a 8.5 watt LED bulb is equivalent to a 60 watt incandescent bulb. Well, that's like roughly 1/8. That means that if you had a 60 watt LED bulb, it would be roughly 8 times brighter than a 60 watt incandescent bulb, which is pretty blinding. It would be, doing some stupid public math, a 640 watt bulb. Wow.
Oh gosh.
So that's, you'd use
it
that
blinds you.
to advertise Crazy Larry's auto sales weekend. They have the searchlights going, or spot for anti-aircraft batteries or something. I don't know.
I mean, you'd be shining on the moon at that point.
But one of the great things that comes into that this has brought about is for survival gear. for flashlights and things that people use, that they have in their cars, that they take on hikes, that they put on their heads. You can have a very compact, very bright bulb that will last 8 times as long on the same battery as an incandescent bulb with an equivalent light output, which is pretty cool. So
Okay.
all of our flashlights are LED flashlights, and they're bright and they last forever, and I love it.
So instead of your flashlight dying after an hour walking through the woods, you now have 8 hours.
Yep. Yeah, I mean, we all remember going camping as children and setting up the tent in the dark with the flashlights and thinking it was the greatest thing ever until the flashlight died halfway through, and then we were out of luck. And it didn't matter.
The 32D batteries that you had to take with you to make sure you had light.
Yep. Because we were all using ancient incandescent bulbs back then. Your LED bulb lasts significantly longer. So, and I mean, we've kind of gone from the first law of thermodynamics to singing the praises of LED bulbs. The other benefit of them is that the actual physical mechanisms or components do not degrade the same way that the components of an incandescent bulb do. The other benefit that they have over some other energy efficient bulb types like CFL bulbs is that in general they won't set your house on fire, whereas a CFL bulb carries a very real fire hazard risk. Ask me how I know. You ask? Well, it's because we almost had one set our house on fire. And after we called the fire department and they figured out where the source of the burning was coming from, they actually asked if they could keep our CFL bulb, which had scorched a hole in the base, melted through the plastic. They asked if they could keep that as a training aid for their fire department.
When was this?
And we made them an offer, and they rejected our offer, and so we told them no. But no, I'm kidding. This was back 6 or 7 years ago. Since then, I've never purchased a CFL bulb. If you want to do that, that's fine.
Aren't those the ones that you also had to have a hazmat team use if it broke? And
yeah, because they have mercury in them.
Mercury vapor and
yeah, they're pretty nasty if they break.
Do bad things to you.
Yep.
Okay, so there are other measurements of energy, but I think we've belabored the point of the LED bulbs to the point where we probably should be wrapping the podcast here pretty soon.
Hey Tim, that's another good idea for a band name is LED. LED.
or belabored LED.
Like Led Zeppelin or something cool like that.
Nah, that wouldn't work. It just sounds nice try, Johnny. That's
okay.
Destined to failure.
It just came to me.
Yeah, well, get some sleep, huh?
It is late here.
Okay, so on other units of energy, we can really briefly touch on a calorie is but they all convert back to joules eventually, right? The idea of a calorie is the ability. It says the heat. It's the amount needed to raise 1 gram of water 1 degree centigrade.
Yeah.
So a calorie
is basically an obsolete unit at this point.
Right.
The joule is
the thing. Right. Exactly.
Yep.
Don't tell Jenny Craig it's obsolete.
By the way, when you talk about calories, it's actually kilocalories. It's kcal.
Yes.
Not just calories. So
what?
Yeah, it's 1,000 calories.
Yeah. That explains the gut, Tim. That explains the gut.
Yeah, this changed. I've got to stop eating.
So when you have a food that's only 100 calories, it's actually 100,000 calories. Think about that for a minute.
If we told people that, everyone would feel so gluttonous.
Well, we are telling people that.
Yeah, that's right. There you go. So stop eating. Put that Oreo down.
Conversely, your exercise machine that tells you that you're burning 5 calories for having jogged a mile and a half is also measuring kilocalories. So you can feel slightly better about that. You've burned 5,000 calories.
We could go into business, start selling equipment that tells you how many actual calories you're burning. People, feel better using our stuff.
Feel that if you just put on chapstick, that's 5 calories. So I now have to walk a mile and a half to burn off my chapstick. So.
You're not supposed to
questions
eat
about-
your chapstick, Cameron. You're not supposed to eat it.
Hey, he's cutting into
that's
his
what I've been
food
doing wrong my
storage.
entire life.
He's trying to social distance.
That's right.
Petroleum.
During this outbreak, you make do, right?
That's
All
right.
right. Did you have
Anyway.
other energy unit questions?
I don't think so. So. I mean, electricity are different measurements, right? So
Yeah.
they're related in the layman's mind because I am the layman, and they're related in my mind. But the idea
Sure.
of volts and amperage and all that kind of stuff, those aren't measurements of energy. They're measurements of electricity, right? So.
Yeah, it would be worthwhile doing a whole separate thing on electrical measurement and physics and engineering and stuff.
Right.
But yeah, those are essentially circuit measurements.
Right.
So let's really ask a question that people want to know. Does it make a difference if I leave an appliance plugged in or unplugged to save on electricity?
It depends entirely on the appliance and how the appliance is engineered. But in general, if your appliance is doing anything, if it is feeding electricity through a circuit, if it is maintaining a temperature, if it is sitting there with an intermittent motor coming on and off, it is using electricity. If your TV is downloading updates on its Wi-Fi while it's off, it is using electricity and energy. If you don't want that to happen, then unplug the stupid thing. If you don't care, leave it plugged in. Different appliances are engineered differently to have different shutoffs and switches. So it totally depends on the appliance. But yeah, look at whatever your thing is. If it's got a light that's on or blinking, well, it's at least using electricity for something. Possibly a minuscule amount, possibly a large amount. You'd have to look it up. But,
I actually did just look. So I don't know how old this stat is, but it says in the average home, 75% of the electricity used to power home electronics is consumed while the products are turned off. So as an example, it says the average desktop computer idles at 80 watts, while the average laptop idles at 20 watts. So I'd imagine, I don't know how old this thing that I'm reading, I imagine over time these electronic devices have become more efficient with their processes, but they're going to still consume. If it was 75%, let's say 10 years ago, I'd imagine best case scenario, we're talking 50% now.
Yeah, well, I mean, again, it all depends on the specific device, and a lot of them have evolved and changed. And when they talk about idling, that means to me something very different than being switched off. So when my computer is idle, I consider that sitting there displaying the desktop background, but not actually executing any programs. And yes, it idles at some amount of watts. But when it is switched off, my desktop at least is pretty dead. It doesn't do much of anything. I don't know if your desktop is the same. It all depends.
Right.
One other thing that I'll point out is your electrical bill is measured in one other units of measurement here, since we talked about those, and that's watt hours. It's actually kilowatt hours. And it's just what it sounds like. You get billed based on the amount of electricity you chew up over time. And you chew up electricity at a given rate measured in watts. And we talk about how many hours you've spent chewing up electricity at that rate. That's your kilowatt hours, and that's what your bill is, and that's what you end up paying for. So if my computer absorbs half a kilowatt, which it does, and I leave it on for 10 hours, I've bought 5 kilowatt hours of electricity for that period of time, and that's what I'm going to pay for.
Cool. Hey, one other quick interesting fact I just read while you were talking about that. It says, according to Google, this is, by the way, published in 2017.
Oh, yeah, so it's definitely true and correct.
Exactly. According to Google, the energy it takes to conduct 100 searches on its site is equivalent to a 60-watt light bulb burning for 28 minutes.
Wow.
So if you do 100 searches, It's essentially leaving a light on for half an hour.
Was that published on MySpace?
So if you want to
it's
be,
interesting. I thought it meant Google, but I guess when it said Yahoo, it probably did actually mean
so and now that's the energy that's being consumed by Google's server farms, not
Correct.
what you as the consumer are doing. So if you want to be a
Correct.
bit of an eco-terrorist, just set up a little bot on your computer to do Google searches over and over, send the Google server farm into overdrive, have them consume all the electricity, and yeah, there we go.
Right. There we go.
Every time you do a Google search, a spotted owl dies, is really what it comes down to.
Take that, nature.
Wow. Peter should really get listened to our podcast now.
I'll do that, and then I will taunt some lettuce.
Worst ways to die. You guys already did that, right? So
Yeah,
We did.
But we could do
killed by Google search didn't make the list, but oh well.
could make a new set. It's a deep topic. Lots to
Spotted
mine.
owl dying by Google searches.
Yeah.
That didn't make top 10? What the heck?
I'm sorry, Johnny. We let you down.
All right. Well, on that unfortunate note, we will leave this podcast and
Do we
and
ever
ask
leave
you.
on a fortunate note?
No, we never do. So
It's
we'll
entropy.
just entropy. Please come back and don't judge us. So until next time, you can subscribe to the podcast if you want to, I guess, and stay safe.
But only search it once.